Hey, hello, welcome. We're in Advanced Algebra 2. We're talking about lines that cross, and they got like inequality symbols now, all sorts of things. This is called the systems of inequalities because they're inequalities, they're not equal, and there's a system, meaning there's more than one of them. All right, so here we got example one. We got a couple inequalities together. I'm going to remind you of some of the basics as we go along. Nothing should probably be terribly shocking to you. We got to graph these. I mean, the grid below is a hint, if nothing else. All right, first up, I'm going to take that top equation and solve it for y. So, subtract the 3x from each side and then divide by 4. So y is greater than negative 3/4 x plus 3. Remember that everything gets divided by 4. Let's graph it. So, we got ourselves a y-intercept of 3, and then a slope of negative 3/4. So I made some dots. And then I'm connecting the dots. Now, please, I know this is somewhat, hypocritical. Please be generous about the fact that my dashes here are clearly not drawn with a straight edge. It is somewhere between incredibly hard and impossible to use a straight edge on an iPad screen. So, my apologies about not showing what I demand in class. I hope you understand. It's a calculated decision to give you the best experience I can here. Okay, so we got dashed line. That's because it's a greater than with no equal sign. Dashed line is kind of like an open dot on a number line graph, meaning, well, that line's there, but that's not really part of the answer. All right, now it says greater than, so we're talking about the stuff above. Now, back in Algebra 1, you almost certainly graphed these where you would graph a line and then shade. I'm not going to shade yet because there's also a second inequality. Let's go to it. So we got negative 4y is greater than or equal to negative x minus 8. Subtracted the x from each side. Then go ahead and divide by negative 4. So y, we got a positive 1/4 x and positive 2. Now, notice though that the inequality sign switched, right? It flipped. It was greater than or equal to. Then it became less than or equal to. And that's because we divided by a negative number. A little reminder about how inequalities work. You've seen it before in this class. You've certainly seen it in prior years. Just a reminder for you. Okay, so graph it. Y-intercept of 2, slope of 1/4. Boom, chicka boom, chicka boom. This one's going to be a solid line, and here my inability to use a straight edge is actually even more apparent. It says less than or equal to by the time we're done solving for y, so we're going to shade below. And I'm just drawing arrows now to help you kind of get settled here. And then we need to shade where it's the arrow side of both lines at the same time. And that's what we're talking about right there in the right hand chunk. That's the answer. You don't have to draw the word answer and then an arrow. I'm just trying to highlight that right there is actually the answer. You need the solid line, you need the dashed line, and the shading. And those are the battles here. Okay. That's the first example. That's meant to be, relatively easy-ish, compared to, at least. The second example, oh, look, 3. Okay, this time I'm going to number them just so it's clear which one I'm working off of. The numbering isn't important. The understanding what I'm doing is important. Okay, so we got to move the 3x over. Then we're going to go ahead and divide by 2. So we got negative 3/2 x plus 6. All right, so then we're going to graph that. Y-intercept of 6, slope of negative 3/2. Put some dots down, dot, dot, dot. I had a cat named Dot, Dot once. Anyway, you got a dashed line. Again, I didn't use a straight edge. You need to. I'm sorry. I promise to do it whenever I do it on the board for you. Okay. Shade below this time. Now, don't really shade yet. Hold it. But arrows indicating it. I potentially put too many arrows down. The number of arrows you use to show isn't important. Hey, let's move on to the second inequality. So we're solving that bad boy for y. Not sure why it's a boy or why it's bad, but we add the 2x, then we divide by 5. Remember, everyone gets divided by 5, and Oprah style, right? Okay, and then positive slope of 2/5. There we go. Got some arrows on the end. And this is going to be greater than. So dashed line, not solid, and arrows above. The arrows are just meant to be a guide for you for later, not terribly important. Here we're solving for y, so subtract the x and then divide by -1. That does cause the inequality to flip around. So notice that flipped around there. And so we're talking about a slope of 1, a y-intercept of 1. That's a lot of dots for me. Certainly you don't need more than, 3 is a good number. 2 will technically work if you're careful. And then, especially with a solid line, you can tell I'm cheating and not using a straight edge. I apologize, I apologize, I apologize. It's just not actually possible. Okay, arrows below because it says less than or equal to. Good times. I need to shade the area that is on the arrowy side of each of the lines. Right, on the correct side of the lines, the arrows indicate which side is the correct side. That ends up, in this case, being inside the little triangle. Boom. And the answer's there. And again, the word answer with an arrow is really just meant to be demonstrative right now. If you just shade, I know exactly that's the answer. Nobody writes the word answer with an arrow. And now some of you are going to start to be annoying. Oh well, okay, so here we go. We got the answer there in between each of the lines. And that's it. So this first chunk, you got to draw some lines. You got to remember how slope and intercept work. And, it's doable. Now, this is real work. Craig Browning bakes cookies for the elementary school cookie sale. His chocolate chip cookies sell for $1 a dozen. His oatmeal brownie cookies sell for $1.50 a dozen. You can read. By now you may have had a chance to read. We need to begin by defining some variables here. So one of them is going to be for, well, they got choices, right? One of them is going to be about the chocolate chip cookie situation. One of them is going to be about the oatmeal brownie situation. So I'll have one variable be the number of dozen of chocolate chip cookies, and the other variable will be the number of dozen of oatmeal brownie cookies. Quick issue here. Make sure when you're making the variables that you include the word number, unless it's by definition a number. Almost always you just need to use the word number. Don't write down cookies or chocolate chip cookies because you are not going to actually graph cookies, although that's a very tempting and tummy-yumming thought. Also in this case it's about the number of dozens. If you keep reading, it's about dozen each time, it's about dozen each time. So in terms of units, it's dozens, which is easier to count than a meter, at least. Okay. Define the variables. Now, for the next thing, I have to move on to a new slide. You, of course, can just look up on your page, which is much better. You need to write the constraints, and each constraint comes from each idea. So basically, you kind of want to use up the sentences in the problem. However, they're not always written exactly where one phrase is a constraint and, etc. I'm talking too much. So let's try. One says that he can make up to 20 dozen chocolate chip cookies. So X would have to be less than or equal to 20. One of them says he can make up to, 40 dozen? 40 dozen oatmeal brownie cookies? So that's what we're talking about. Y is less than or equal to 40. Also says that you can make a total of up to 50 dozen. So here we're looking at the sum, the total, being less than or equal to 50. Now, that's great. Also, the number of oatmeal brownie cookies, what's the phrase? The number of oatmeal brownie cookies will be no more than 3 times the number of chocolate chip cookies. So, number of oatmeal brownies, Y, no more than, which means less than or equal to, 3 times chocolate chip cookies. Okay, those are the constraints that are kind of written down in the problem. As I was trying to say before I realized it was dumb to say it at the time, the constraints come from the phrasing of the wording. Sometimes, on a super nice day, or when you're super awake, it will seem like they jump out at you one phrase at a time, or even better, sometimes one sentence at a time. Sometimes they will seem mished and mashed up together. You do need to separate the writing from the ideas behind the writing, and a constraint is an inequality that describes, one of the ideas in the writing. Those are the ones listed, but there's more, which is and this will seem obvious to you, but it actually is a constraint, you can't make negative numbers of cookies. Nor should anybody ever try to make negative numbers of cookies, because they are a universal good in our universe. So the x is greater than or equal to 0, y is greater than or equal to 0, not stated in this problem, definitely necessary. There might be scenarios where negative numbers are reasonable given the situation. Most often, they're not possible. So, if you're going to refuse to think about it, it's best to just add those last two automatically. Even better would be thinking about it and trying to see if negative numbers are potentially an option in life. But, whatever. Okay, now we got to graph them. So, I used x and y as my variables. You don't have to use x and y. I just did because it would be easier to see on a graph. And then I'm labeling the axes. I got to go to 50, so going by 5s just seems like the best plan. I guess you could go by 3s. There's a thing that engineers often use called the 1, 2, 5, 10 rule, which means you should always scale by 1s, or by 2s, or by 5s, or by 10s, or multiples of those. So like 20's great, 50's great, 100's great, but like 30, not really a great number to scale by. That's just a rule for style points in life. It's not a hard rule about math. So I went by 5s. You do what you like. Just trying to fit it in. Okay, so the first constraint is less than or equal to 20 for the x. So there's that line. And then the second constraint is less than or equal to 40 for the y. So there's that line. I'm going to add several lines, as you might imagine, so I'm limiting my arrows. Otherwise, I'd have arrow overload. Also, I don't have enough colors for each constraint. So those are the first two constraints. The third constraint is that the total has to be less than or equal to 50. This one's easiest if you just do the intercept version. If you want on the side, you can solve, for y and do slope-intercept version instead. It's just fine. But if you just, 50 and 50 is the intercepts, and connect them, boom, has to be less than or equal to. And then the last constraint given in the situation is that the number of oatmeal brownie can't be more than 3 times the number of chocolate chip. Y is less than or equal to 3x. So y-intercept is 0, slope of 3, which is hard in this case. So instead of doing 3 over 1, you think of it as 15 over 5. But either way, less than or equal to. Now, there's the other two constraints, which I'm going to draw. It's going to seem silly to draw them because they're on the border of the graph. But there we are. And the feasible region, which is what we call all of the possible answers, is inside all of those arrows at the same time. So the magic vocabulary word is called feasible region. It's the thing that you can do if you were so motivated. What is a little bit interesting here, just before we move on, just a tad bit interesting, is noticing that this constraint, the x is greater than or equal to 0 constraint, that's not actually used. That doesn't actually make part of the border. And there's no guarantee that any given constraint ever actually makes part of the border. So in this case, for example, that's not there. I mean, the line is there, but without that line, the feasible region... Excuse me, I'm so sorry, I just had iPad fail. Without that line, that feasible region would still be the same. I know that sounded awkward because I left in mid-sentence. Sorry about that. Okay, now, moving on. We have to create an optimization function. This means what do you want out of the situation, and the school wants to make money. And then we're going to have to graph it. So, I'm not sure why I highlighted graph first, but okay. So we're going to have to graph this. And since I'm going to have to graph it, I know they make $1 for each dozen chocolate chip, and $1.50 for each dozen oatmeal brownie. So 1x plus 1.5y equals 30. And I just made up the number 30. I'm trying to make a number that is going to be kind of reasonable-ish to graph. So 30 works because if you graph it now, which would come next. And again, this is the easiest way to doing this is by graphing with the intercepts. If you graph it now, and this is going to be slightly awkward, but let's see what we can do. So we have 30, so I'll graph it in green here. We got boom, an intercept at 30, 0, and then we'll have an intercept at 0, 20, and then graphing it. And again, this is going to be massive straight edge fail. My sincerest apologies, but boom. That is the line of all the options they can have where they make $30. We would like to make as much as possible, so maybe we can build it out. And so, for example, if we doubled all the things, if we had 40 over here and we had 60 over there, and my straight edge fail is going to increase even more now. Boom. That's a parallel line to the one before, and that has them making $60. Remember, the 30 was just made up and didn't mean anything. They're parallel lines. So what you want to do is you want to take this line and slide it up and down until you leave the feasible region, and you find the spot that's the last spot in the feasible region. This, if you slide those parallel lines up and down, that corner I just circled in green, that is the last spot in the feasible region. So we need to find that spot right there. So to do that, oopsie daisy, that's a lot of information. Sorry about that. To do that, we're going to go ahead and, bear with me as we put that back, we're going to go ahead and solve for that corner I just showed you. And that comes from these two lines, y equals 3x and x plus y equals 50. Now, I wrote equals this time because it's actually where the lines themselves cross, not this magic space below or above the lines. So this one's pretty easy to solve. You substitute the 3x in for the y, so you end up with 4x equals 50, and then x equals 12.5, and so then y equals 37.5. That is the bestest spot. So, answer the question, the school should sell 12.5 dozen chocolate chip cookies and 37.5 dozen oatmeal brownie cookies. But there are two questions. One was how much should they sell? The other one was how much will they make? Boom. They would make a profit of $68.75 with that amount. All right. These problems take a long time. Each of the individual pieces is not so hard. Putting it all together is, it's a lot. And then this optimization line thing, the idea how they're parallel, that shouldn't blow your mind, but that takes a little while to get used to. And then kind of sliding it up and down. When I'm doing it on a real graph, I use a ruler. So, sorry, go back to here, like these green lines. When I do it on a real graph, I'll use a ruler and slide it up and down in a parallel manner to see where I'm leaving that. So if you're at all confused about why that green point is circled, you should totally take a ruler, put it on one green line, and then kind of slide it around without changing the angle of the ruler. That should give you a good show on why that works. Hey, thank you for watching. It's been a while. This is not terribly hard to do. Some strange spots here and there, though. Please let me know if you have any questions, and as always, thank you for watching.